Greetings, this is Professor Roman. Welcome back to my lecture series called Transition to Advanced Mathematics. It's time now that we started to examine mathematical logic. We discussed the fact that to study advanced mathematics, it's vital to have some background in the art of logical thinking. For us, this means examining the very rudiments of two forms of logic, known as the propositional calculus and the predicate calculus. In case you're worried about the term calculus, this has nothing to do with integral or differential calculus. The term calculus means any system of reasoning. The propositional calculus is by far the simpler of the two calculi, and while it provides some very important insights into the process of logical thinking, it's unfortunately not powerful enough to express all of the ideas that are required to do mathematics. So we will turn to the study of predicate calculus when we are finished with the propositional calculus. About 350 years before the birth of Christ, the Greek philosopher Aristotle began what we might refer to as the discipline of logic. Aristotle's primary goal was to set down rules by which it is possible to tell whether or not a given argument is valid. But surprisingly, modern logic can also be used in ways that Aristotle never could have dreamed of. For example, it can be used to design circuits for computers. But our central interest, of course, is in the art of logical thinking and evaluating arguments for their validity. Just as an example, and I think I gave this example to you before, here is a valid logical argument. If today is Friday, then I must go to the bank. Today is Friday, therefore I must go to the bank. On the other hand, this argument, if today is Friday, then I must go to the bank, therefore today is Friday, is not valid. And it's important to be able to see that one of these arguments is valid and the other is not, without having to spend too much time. It should become more or less second nature, at least for simple arguments like these. Now, Aristotle knew that the logical structure of statements and arguments could be made more apparent by stripping them of irrelevant details. And that can be done by putting the arguments into what is called symbolic form. So to illustrate symbolic form, we would first define as applied, say, to this argument, we would first define two variables. We'll let P stand for the phrase, today is Friday, and we'll let Q stand for the phrase, I must go to the bank. When we make the substitution, placing these variables into the argument, it becomes if P then Q, P therefore Q. This is not full symbolic form because we still have some English here, but it's a big step forward. Aristotle showed, as we will do as well, that any argument of this form is valid regardless of what the variables P and Q represent. You could put any phrase in for P, as long as you put the same phrase in for both P's, any phrase in for Q. It doesn't matter whether the phrase is true or false. You can put anything you want in there. If the moon is made of green cheese, then 1 plus 1 equals 7. The moon is made of green cheese, therefore 1 plus 1 equals 7. That is a valid argument. Now, nobody said the conclusion was true, but what we do say is that the entire argument is valid if the moon is made of green cheese, then so on and so forth. So there's an assumption that the moon is made of green cheese. Under that assumption, this argument is valid. Okay? But it's the logical structure of this argument that is the key, not the semantics, not the meaning. It has nothing to do with Friday or bank or anything. It's just the structure, not the meaning, that makes this valid. In fact, this argument is very famous. It's probably the most famous of all valid arguments, and it has a Latin name, Modus ponens. This is a name you should learn. It translates roughly as in the manner of asserting, or some such English phrase, which is of no help really, but modus ponens is its name. Incidentally, on an historical note, I think it's interesting to observe that people of Aristotle's day considered the ability to argue logically to be a very high art form. In fact, in Aristotle's day, groups of teachers who were referred to as sophists would travel like wandering minstrels, teaching students for a fee how to argue logically on a vast array of subjects. Not just mathematics, but natural science, philosophy, law, and so on. And the sophists would also engage in public debate and would often command large fees for their appearances. How times have changed. The basic object of study in the propositional calculus is the proposition, also called a statement. In fact, propositional calculus is sometimes called statement calculus. If we want to borrow from the language of chemistry, the atoms of the propositional calculus are called simple statements, and I'll give you a definition of that in a few minutes. And simple statements are bonded together by what are called the 5 basic connectives into, again in chemistry, molecules. And they're called compound propositions or compound statements. So without the chemistry, simple statements are combined using connectives to produce compound statements. So let's go look at the formal definitions. These are the 5 basic connectives. Each one has a name: conjunction, disjunction, negation, conditional, and biconditional. But this is just the name of the connective. It's not the phrase you use when you place a connective in a sentence. Conjunction would be read and, disjunction is or, negation is not. The conditional is read in 2 different ways: implies or if then, and the biconditional is read if and only if. And these are the symbols. You have what looks like an upside down V, unadorned, there's no serifs. Disjunction is a right side up V. They're not really V's. It's not the letter V, but it looks similar to a V. Negation has 2 different common notations. I prefer the first one, and I will use it instead of the second one, because the second one is a common notation for other things in mathematics, such as similarity or equivalence relation and other things. I'm not aware that this symbol is used in any other common way in mathematics. I don't think it is. So I think that makes it a little bit better symbol for negation. Implication, the conditional is a double arrow, although some people would use a single arrow. And the biconditional is a double arrow pointed in both directions. Okay. A simple statement or simple proposition is a sentence written in some language and or using symbols that has a truth value. It's either true or it's false. No ambiguity. But simple statements, by definition, cannot contain any of the 5 basic connectives. A compound statement or compound proposition is a sentence that's composed of one or more simple statements linked together with at least one of the 5 basic connectives. And I will probably use the term statement or proposition unadorned for either type, simple or compound. Here's an example of some simple statements. All birds are animals. In case you've studied the predicate calculus, you will recognize the word all as the universal quantifier. And so in the predicate calculus, this is not a simple statement, but for now we're just dealing with the propositional calculus. So this is a simple statement. Today is Tuesday. 2 plus 2 equals 5. It is raining. These all have a truth value. They're either true or they're false. No ambiguity. And they do not involve any connectives. So they're simple statements. Notice that a simple statement must have a truth value, but that truth value can change. So today is Tuesday is only true on one day of the week. It's false on the other days. But nevertheless, at any moment, it has a truth value, true or false. Another thing to observe is that while simple statements must have a truth value, we may not know what that truth value is. And I made up this kind of ridiculous example just for fun. Lucius Tarquinius Superbus had a foolish hanging of his nether lip. This, by the way, is from Henry IV, Part 1. Superbus was the last king of ancient Rome. He died in 495 BCE, before the Common Era. So it's rather difficult to find anyone these days who could tell you whether who knew him personally, who could tell you whether he had a foolish hanging of his nether lip or not. While this statement is either true or false, we don't know which it is. Okay. A more apropos example would have been something like, the Goldbach conjecture is true. We don't know if it's true or it's false. It's one or the other. We don't know which. But it does have, that statement does have a truth value. That's either true or it's false. On the other hand, these sentences are not statements because they don't have a truth value. No smoking. That's a command, if you will. It's not subject to truth value. You see a sign on the wall that says no smoking. It just means do not smoke. It's an order. Do you have a red balloon? That's a question. So while someone might answer it true or false using those words, they're really saying yes or no. And so this doesn't have a truth value because it's a question. Here are some compound statements, and I put the connectives in bold this time. I'm not going to do that in future. Nobody does. But just so you can see it clearly, see the structure. It is not raining. this is a compound statement. It is raining is a simple statement, but now there's a connective here, so that becomes a compound statement. It is cloudy and it is raining. This is the conjunction of two simple statements. It is cloudy and it is raining. It is not raining or it is cloudy. You've got two connectives here. If it is raining, then it is cloudy. This is a conditional statement. X equals 1 if and only if x squared equals 1. This is a biconditional statement, so it has the biconditional connective. Oh, by the way, something I should have said. You have to learn this table, and you have to learn it quickly. You have to learn these terms. You have to learn the expressions, how they're expressed, and you must learn the symbols. It's just part of the understanding of logic. I'm going to use these words a lot, use these symbols a lot. You need to be comfortable with that. Another example, the conjunction of the statements, I am a student of logic and I like to dispute, is I am a student of logic and I like to dispute. The disjunction would be I am a student of logic or I like to dispute. Taking the negation of a statement can sometimes be a little tricky. Conjunction, disjunction, pretty straightforward. Implicate the conditional and biconditional also. But negation can get a little bit tricky. Let me give you some examples. This one's pretty straightforward. The negation of the statement Mary is a good student is Mary is not a good student. The negation of the statement 2 plus 2 equals 5 is 2 plus 2 not equal to 5. But look at this one. The negation of the statement some cars are green. When I ask students in a classroom what the negation is, I will get a split answer. Some will say no cars are green. Some will say there is a car that's not green, and that is not correct. One has to be very careful here. Some cars are green. To negate that, there can be no green cars at all. If this is a little confusing to you, imagine a parking lot and the statement some cars are green means there's at least one green car in the parking lot. Doesn't mean they're all green, just at least one. How would you negate that? How would you make that statement false? You would pull out all the green cars. There may only be one. So the result would be there are no green cars. No cars are green. Note carefully that the negation of some cars are green is not some cars are not green. Think about the parking lot again. You've got 100 cars in the parking lot. If there's one green car, then some cars are green. To negate that, you have to remove that green car. Now you have no green cars. Before you remove the green car, this is still true. Some cars are not green. So you have one green car and 199 other cars of the other colors. Both these statements are true. Some cars are green and some cars are not green. So they're not negations of each other. Here's another example that can be a little bit confusing. All cars are blue. To negate that, we can do it in several ways. Not all cars are blue. Some cars are not blue. There is a car that is not blue. It would be incorrect to say the negation is no cars are blue. That is, in fact, the extreme opposite. Think again about the parking lot with 100 cars. They're all blue. To negate that, all you have to do is remove a single car that's blue and replace it by a car of some other color. Not all cars are blue. Some cars are not blue. In that case, one car. There is a car that's not blue. Okay. But to go from all cars are blue to no cars are blue, you got to remove all the blue cars and replace them with something else. I would strongly urge you to think about these two examples until this becomes second nature to you, until it becomes obvious, really, or clear. It's very important. You might be surprised at how many people are confused by this. Something else I should point out: if you are a student taking an exam and a professor asks you on a test to negate a statement, you can always just place the phrase, "It is not true that," in front of the statement. But my guess is that that's not what the professor has in mind. It's not what I have in mind when I ask that question. I want the negation integrated into the original statement, not just placing "it is not true that" in front of it. Anybody can do that, even if they don't understand what they're doing. So that's not the point here. My goal as a professor is trying to see if you understand the concepts. So you should be careful when you answer a question that says what's the negation of a certain statement. Okay. It's also important to point out that spoken languages, such as English, can often be imprecise, and that is a problem in converting a sentence in English or any other language to symbolic form to expose its logical structure. It can become a little ambiguous, not because of the mathematics, but because of the semantics of the language. Let me give you a simple example. This sentence, x squared greater than or equal to 0, but y is less than 0. But is not one of the 5 basic connectives, but the language here the intention is that this is a conjunction and x squared greater than or equal to 0 and y is less than 0. So that's how it would be translated into symbolic form. This would be the conjunction. In English, the word but is not synonymous with the word and. There's a somewhat different intonation here. It's something like x squared is greater than or equal to 0, but guess what? It's not true that y is greater than or equal to 0. Y happens to be less than 0. So there's sort of a subtle difference there between saying x squared greater than or equal to 0, but y is less than 0, and x squared is greater than or equal to 0, and y is less than 0. But we have to remove that subtle intonation when we're looking for logical structure. There are other terms that could be used here, other words that also would be translated as conjunction. For example, x squared greater than or equal to 0, however y is less than 0, or nevertheless y is less than 0, or whereas y is less than 0. So there are many possibilities. A conditional statement, P implies Q, or if P then Q, is often phrased in English in a variety of ways. If P then Q is the standard way, so is P implies Q. But you could also say, and you will see this, P is sufficient for Q. P is sufficient for Q. Something to think about here until that seems to make the same, give the same meaning to you as P implies Q. P is sufficient for Q. Q is necessary for P. This is saying that when P happens, Q must happen because Q is necessary for P. P holds only if Q holds, and Q whenever P. I don't think I've ever used number 6 here in my life. Certainly reasonable, but I just have never found a need to phrase it that way. But the others I've seen many times, and I've written myself many times. So you do need to have a feel for the fact that these are all the same. Okay, so it may take a little time. The biconditional also can be phrased in different ways. The standard way is P if and only if Q. Another possibility is P implies Q and conversely. We'll talk later about the converse, and so this may become clearer. P is necessary and sufficient for Q, so that's a combination of 3 and 4 here. So these are also phrases you need to become comfortable with. As I mentioned, Aristotle realized that it is easier to see the logical structure of a compound statement or an argument by placing it in symbolic form. So simple statements, the atoms, if you will, get replaced by variables, and I'll generally use letters like P, Q, R, and S. And the connectives get replaced by their symbols from the table. So let's look at a couple of examples. I like studying and I like going to the library. To convert this to symbolic form, you would say, let P be the statement, I like studying. Let Q be the statement, I like going to the library. Then conjunction, remember, is the upside down V. So the symbolic form is P and Q. You read this as and, P and Q. To get the symbolic form of I go to the movies, that should be if I go to the movies, then I will probably eat a lot of popcorn. So P is the phrase, I go to the movies, and you will see it done this way often with a colon. Q is, I will probably eat a lot of popcorn. Then the symbolic form is P implies Q. The symbolic form of the statement, today is Friday or it is not Saturday. Notice there are 2 connectives. The simple statements are P, today is Friday, Q, it is Saturday. Symbolic form, P or not Q. Let P be the simple statement, I study hard, and let Q be the simple statement, I will get a good grade in this class. Then this statement, written in symbolic form, translates into English as, if I study hard, then I will get a good grade in this class. And if I do not study hard, then I will not get a good grade in this class. In writing English sentences, you don't use parentheses except for parenthetical remarks. But if you were going to do so, the parentheses would go like that, with the and separating the 2 separate phrases. this example does illustrate that symbolic form can be far more compact and, in that sense, much easier to read than an English sentence or sentence in any other language. The real point is that the symbolic form clearly exposes the logical structure of the statement. And it does so much more easily than its English counterpart. When the sentences get long, it becomes a lot more difficult to see the logical structure. So, one of your main tasks in learning this material is to be able to go back and forth between English and symbolic form in both directions and get to the point where that becomes a relatively easy process. If the symbolic form is very complicated, and we'll see some examples when we look at the ZF axioms of set theory, it can become rather difficult to untangle the symbols and write a decent sentence in the English language. So it does take some practice. So we've defined the 5 basic connectives. We've given their names and their symbols, but we haven't really discussed their logical meaning. For the most part, is pretty obvious, but not entirely, as we'll see in a minute. The way we define the logical meaning of a connective is with a truth table. The table tells us precisely when a compound statement is true or false. A compound statement that involves the connective is true or false based on the truth value of the simple statements that are part of the sentence. We can't use logic to give us any insight into the truth value of a simple statement. It is raining. That's not an issue for mathematics or for logic. You just look out the window. So we're talking about truth values for compound statements given the truth value for the simple statements. So let's look at the connectives. This is the meaning of negation in this, as laid out by this table. When a statement is true, a simple statement, or actually could be compound, is true, its negation is false. When a statement is false, its negation is true. This captures the mathematical meaning of negation. And fortunately, it coincides with common usage. Conjunction has this truth table. P and Q, by the very nature of the word and, is going to be true when and only when both P and Q are true. So that's the first row of the table. There are falses in all the other rows, all the other possibilities for the truth values of P and Q. So this captures the essence of the conjunction and. Okay. Disjunction is or, and the table looks like this. We have the disjunction is true as long as at least one of its participants, P and Q, are true. So when they're both false, the disjunction is false. That's the only time it's false. Now, we have to be careful here because there is an alternative meaning to the word or in the English language. And so we need to clarify a little bit. There are two interpretations for a phrase such as P or Q. The inclusive or is P or Q or both. The exclusive or is P or Q but not both. Most people understand the word or to mean the inclusive or, but every once in a while you will find someone who thinks of it as the exclusive or, and so that can be a slight issue. In mathematics, the disjunction or always means inclusive or. So P or Q is true when both are true, as well as when only one is true. And that's what it says in the table. That's why we write the tables, to remove any possible ambiguity, to basically remove any language, like English or whatever, so there's no chance of any confusion or ambiguity. The exclusive or does play a role in mathematics. It is generally denoted by the acronym XOR or EOR. Here is its truth table. So the difference is that when both are true, the exclusive or is false. Disjunction always refers to inclusive or. The exclusive or plays a role in computer science, for example. There are circuits that are designed to mimic the behavior of the exclusive or. The biconditional, P if and only if Q, the intention here is that P if and only if Q is true exactly when both P and Q have the same truth value. So the first row is true and the last row is true. I saved the best for last, so to speak, and that's the conditional, because this tends to be the most confusing of the five connectives. The conditional, this is most often read P implies Q or P, if P then Q. It's also just referred to as implication. The statement P here, the statement that comes before the arrow, is called the antecedent of the conditional. The statement that comes after is called the consequent of the conditional. Those are important terms to know. The truth table for the conditional looks like this. And the main controversy, if you want, in this table comes from the third and fourth rows. According to this table, whenever the antecedent is false, so those are the last two rows, the conditional statement is true, regardless of the truth value of the consequent. So for example, 1 plus 1 equals 3 implies 1 plus 1 equals 4 is, believe it or not, a true statement, because the antecedent is false. 1 plus 1 equals 3 implies the moon is made of green cheese. True statement, because the antecedent is false. Well, there have been many different attempts to justify, to explain the last two rows of this table, because it does perhaps seem to you to be ridiculous. The first two rows, nobody would quibble over. True implies true, that's a true statement. True implies false, that can't happen. This has got to be false. So if P is true and Q is false, the implication P implies Q would say something true implies something false, and that should not be. So that's a false statement. Okay. How do we sort of justify the last two rows? Well, there's a couple things you could do. You could say, well, I don't want to know, I'll just memorize the table and leave it at that. You can certainly do that. I would have to say that's not the best attitude for someone who wants to study mathematics. Another way you could look at it is, well, if I'm trying to establish something of the form P implies Q, establish that it's true, I'm not going to do so when P is false. In other words, it's not that relevant. No theorem that I've ever seen says that if 1 plus 1 equals 3, then 1 plus 1 equals 4. Let's prove that. The objection comes immediately, well, 1 plus 1 equals 3 is not true, so why are we wasting our time? But it's better to think of it, for example, in the following way. There are 4 choices that you could put here in the last 2 rows. 2 trues, 2 falses, true, false, false, true. 4 possibilities. This is the only one that doesn't lead to something that seems quite ridiculous. Here's one way to look at that. I think I put another way in the exercises. The statement P implies P feels like it should always be true, regardless of the truth value for P. P does imply P. If P, then P. Okay? One could dispute the veracity of a statement like, if all cars are blue, then all cars are blue. But that just wouldn't hold, wouldn't go over very well. If all cars are blue, then our cars are blue. That, that certainly seems like a true statement. Okay. Another way to say it would be, assuming that all cars are blue, then all cars are blue. I don't think anybody would argue with that. They would argue with the assumption, but they wouldn't argue with the truth value of the entire statement. Okay. If you can accept that, then it should also seem pretty reasonable that this conditional, P implies P or Q, should also be true. If P implies P is true, then this sort of gives you more freedom. P implies either P or Q. You say, yes, well, P implies P, therefore P implies either P or Q. So here's a sentence, for example. If all cars are blue, then either all cars are blue or 1 plus 1 equals 2. Note here that P, which is all cars are blue, is false. Q, 1 plus 1 equals 2, is true. Okay. So the antecedent here is false, but the consequent is true. And that's all of this. Okay. And this is a true statement. So that kind of helps indicate why you certainly, which row is this? False, true, so that's this third row. You certainly don't want to put an F here, because then this would end up being a false statement. So we need a T here. One of the things that I think could lead to confusion with this is that there's a difference between the truth value of a conditional statement, P implies Q, and the truth value of the consequent. Okay? They're not the same concept. So this implication, 1 plus 1 equals 3 implies 1 plus 1 equals 4, the whole conditional statement is true. The consequent is false. There's nothing wrong with that. Even though the consequent is false, the conditional is true because the antecedent is false. So again, this is something that you should try to come to grips with, but in a way it's not critical because we don't start statements, theorems in mathematics by assuming something's false unless we're trying to prove something by contradiction, which is another story we'll get into later. So false assumptions are not of much value in general, okay, unless we're trying to contradict them. Okay. All right. We now know the truth tables for the 5 basic connectives, and I'm sorry to have to say it, but you do need to memorize those tables. They are the building blocks by which we construct truth tables for compound statements. Example, what is the truth table for the statement P or not Q? Well, we would begin to construct the table. We need a column for each of the variables P and Q. So that's what the first 2 columns are. The last column is the one we're interested in forming, but typically it's best to insert intermediate columns to help avoid making a mistake. If you want to do this kind of thing without doing intermediate columns, that's up to you, but you will increase the chance that you make a mistake. Okay. So the third column here, we need the negation of Q, so we write that column. Now this is the disjunction, or, of the first and third columns. We can now ignore the second column. In fact, for practice, when you first start doing this, you may want to cut out a little piece of paper so you can put something on top of that column, and so you don't accidentally use it. But now the disjunction, remember, is true unless both pieces are false. And as you look through this first and third columns, the only time both P and not Q are false is in the third row, which is why there's an F in the third row. The other rows are all T's. Okay. How about the truth table for Q implies P and not Q. Column for P, column for Q. Want the negation of Q, so column for that. Conjunction of P and not Q is the conjunction of the first column and the third column. So that goes here. You should see now why it's important to be able to take conjunctions without having to look at the table for the conjunction. And then the implication pieced together here. A little bit of practice with this should make you fluid in it. It's not that bad, really, once you have a firm grasp on the 5 basic connectives. Okay. Here's another example, R and Q, if and only if P and Q. P, Q, and R. I need a column for each one, the table grows in size as the number of variables grow. When there are two variables, there are 4 possibilities for their truth values. When there are 3 variables, there are twice as many possibilities, 8 possibilities, so 8 rows. Okay? And I will let you study this table for yourself and do some examples until this becomes comfortable for you. In general, by the way, when there are n variables in a compound statement, there are going to be 2 to the n rows to the table. So these tables can get large very quickly. I don't think we'll go ever beyond 4, possibly not even beyond 3. The principle is the same, so it doesn't really enlighten you any further to do much larger tables. There is something here, though, that's very important to point out. You'll notice when I drew these tables that I put the truth values for the variables in the same order every time. 2 trues, then true, false, true, false. True, 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 false, true, false, true, false, and so on. There is a pattern here that you will get used to as you create the tables. Unfortunately, not all authors use the same order. Some authors will write, for example, here's a table the way I would write it: true, 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 false, true, false. But some authors will do true, true, false, true, false, false. I don't know why. I like this, but it doesn't matter. It's a stylistic thing. Decide how you want to do it and stick to that pattern. And for this course, you would be advised to stick to the pattern I'm using in the book. One thing that you have to be very careful about is that when you take a test and one of the questions is construct a truth table, the person who is reading your solution is quite likely to look at only the last column, okay, and not look at the entire table. If, for example, the question said, write the truth table for the conditional, and if the grader looks at only the last column, you see these last columns are different, even though both truth tables are accurate, because the order of the rows is different. So you run a risk that your truth table will be marked incorrect, even if it is correct, because the grader didn't check the order that you placed the rows in. So when I instruct my students in Math 13, I say, you must use this order for your truth tables. You must. It's a matter of self-preservation. Use the same order that's in the book, so that when a grader looks at your truth tables, they only need to look at the last column to see if it's correct or not. To find the truth table for the statement, if x squared is greater than 1, then either x is less than 1 or x is greater than 1. This word either, that's an embellishment that is not necessary. If x squared is greater than 1, then x is less than 1 or x is greater than 1. That's perfectly acceptable. So this is an extraneous word as far as converting to symbolic form is concerned. So we let P be x squared greater than 1, Q is x less than negative 1, R is x greater than 1. Symbolic form, P implies Q or R. truth table worked out here. So we can see that the only time this statement is false is when P is true and Q and R are false. Or that is to say, when x squared is greater than 1, but x is not less than -1, and x is not greater than 1. Okay. So here a truth table is very helpful in understanding the negation of a more complicated compound statement.